Now, the software development process is the backbone of computer science, system engineering, information systems, and software engineering. You'll hear this term quite a lot whenever there's a discussion on software development. This term is not only limited to software, but applies to hardware as well. You quickly realize that if you're developing a large, complex software, it needs to be planned quite extensively to make sure that the project is a success. Just like with most other things in science, engineering, and even nature, the software development process follows a life cycle that is similar to all of these scenarios. The term life cycle is unashamedly borrowed from nature, just like the chicken at your favorite fast food outlet. Its journey into existence starts as an egg. The egg grows according to the rules of nature, and 4 weeks later, we have an adorable little chick. The chick then grows progressively over the course of a few weeks until it becomes an adult chicken. The chicken is then taken to the processing plant and portioned into pieces that are taken to the fast food outlet. The fast food outlet then spices and cooks the chicken to produce that yummy dish that you are guilty of yearning for all the time. That might have gotten you a little hungry, but let's now look at a more fitting description of the life cycle, that of a plant. A plant starts out as a seed. The seed falls onto the ground and becomes a seedling. The seedling grows into a tall and strong plant that then has flowers on it. Bees or wind pollinate it, taking pollen from one flower to another. The flowers then produce fruit that have seeds in them. The fruit that carry the seeds falls to the ground, and the cycle begins again. Now, the software development life cycle is built on pretty much the same principle. Software starts out as an idea, and developers and engineers get to work, fleshing it out into a problem statement. From then, several processes are followed up until we have a fully fledged, common functioning software package. The journey doesn't end there. Users need to be trained on how to use the software package, and bugs need to be squashed from time to time. If you have been paying attention to current trends in the industry, you may have noticed that it is no longer enough to just release a single version of a software package and end there. People now expect software to keep improving over time. That's also a way for you, the developer, to make money as well. Naturally, this means that the journey will still continue as software engineers keep looking at the code repeatedly, adding new features, removing redundant features, and improving the efficiency of the code. This continues until the software is deemed obsolete and is decommissioned. We have already covered bits and pieces of the software development lifecycle right from the start. As you shall see as we progress with the lesson, flowcharts and pseudocode have their own very important places in the software development lifecycle. All of this points to one key aspect of software development, which is so important that if you overlook it, you are likely just setting yourself up for spectacular failure. And it's the golden word: planning. A huge temptation when writing software is to forego planning and just get on with the work. After all, planning seems like a waste of time when you really know what you want to do. In practice, however, it turns out that planning is not such a big waste of time at all. In actual fact, jumping onto a project without planning is what turns out to be a big waste of time. Not far into the project, you tend to get tangled in so many things and you won't know your way around anymore. Planning enables you to make strategic decisions at the right time. It helps you organize your priorities correctly. The more complex a project becomes, the more critical it becomes to plan out your work before you do anything. There are things that can't be skipped, no matter how knowledgeable and experienced you are. Things such as requirements gathering enable you to focus your expertise on the right path. There are several reasons why you need to plan your project. Let's take a look at 6 of the most common ones. The main reasons for planning a project are the following: defining goals, determining requirements, determining costs, creating a timeline, improving software quality, and understanding the project's value. Let's look at each of them in detail. Now, as we said at the beginning of the lesson, a project starts out as an idea. Nothing on paper, no code, no fancy graphic user interfaces, and no users. At this point, it is important that you set the goals that you seek to achieve. Defining your goals will also help you develop the project from that fuzzy idea to something that is clearly defined and outlined with a realistic plan to it. Note the use of the word realistic. Some projects start out with overzealous plans that turned out to be unrealistic. With your realistic plans, your project is more likely to be successful in the end. At the beginning of the project, you also need to know everything that you need to produce a working piece of software. Once you define your goals, you need to work out everything that is required, directly and indirectly, to reach that goal. It can come in the form of a team, equipment, money, expertise, or opinions from the end users. Without planning, you're most likely never going to get your hands on any of this. It is also typical that these requirements change as you progress with your project. Without a solid plan, it is very easy to go over budget and end up with a failed project. One of the greatest determining factors in a project is its cost. Think of it this way. Would you start a business without knowing how much money you need to run things and how much money you're going to get at the end of the day? This simply just doesn't work. If you've ever approached a bank for a business loan, you'll know that the first thing that they ask for is the plan that you have for spending that money. Nobody wants to sink their money into a hole where they're never going to get it out. Even if you don't borrow money from anyone, it's really just a wasteful practice to throw money at things that you don't know how they'll turn out. Planning will also help you to manage costs without sacrificing results. Now, after creating a basic plan and breaking down everything that you need, you will have a stepping stone that you can use to create a timeline of the things that you expect to do. When it comes to large software projects, it is rarely ever a one-man show. Several people need to work on the project at the same time, and this needs to be coordinated. Without a concrete plan or a timeline, there are no deadlines to meet. And as you're going to see as you progress with software development, a perfect finished software product exists only in fairy tales. It is important that realistic targets are set and milestones are observed, and the product is released as soon as is humanly possible. It's no secret that even in day-to-day life, anything that is planned will simply come out better than something that is just done on a whim. It allows you to set the boundaries on your project and know when it is time to stop. It also allows you to be better prepared for eventualities. Sorry to say, but those are quite common during software development. Lots of bugs to squash, changing customer requirements, tight budgets, the list goes on and on. Planning the project keeps you on top of things and allows you to deal with unforeseen things without panicking. Planning also provides you with metrics against which you can test the quality of the product. The end result will be a project that is very close to what you will have planned. It is also worth mentioning here that deviations can and will happen, but they need to be controlled to make sure that the project itself doesn't change into something completely different. Planning allows you to understand the value of your project. Well, it isn't easy to tell from the very start the amount of value that your project will bring. The milestones and deliverables that you set will provide a benchmark that you can keep checking from time to time. It allows you to manage your time properly and keep track of things such as deadlines and costs. In the 75 years of history of programming till date, humankind has developed over 700 programming languages. The interesting thing is that the software development lifecycle hasn't seen much phenomenal development since then. The first conceptual framework for structuring software development into phases came into being around the 1970s in the form of the waterfall model. The first formal description of the waterfall model was cited in a 1970 article by Winston W. Royce. The waterfall model maintained its dominance for well over 2 decades and is still used today by many software development teams. It provided a way to progress through software development in a linear manner, with milestones in the development process, which made it easy to understand and implement. The waterfall model has distinct phases, and each phase has its own distinct activities. Around the 1980s, a fork was developed in Germany, known as the V model, and was used for defense projects. It is basically an extension of the waterfall model in which there is a testing phase for each corresponding development stage. Things started to change when software development shifted towards customer centricity. The flaws of the once really great waterfall model started to show. As with everything that is customer-centric, requirements often change from time to time. This did not quite work well with the waterfall model, which has rigid steps at each stage. Iterative models started appearing around the 1970s to complement the waterfall model's shortcomings. This is what we know today as agile frameworks, which adapt to changes in the user's requirement or development environment. This came in the form of the spiral model and rapid application development. In the 1990s, other models such as feature-driven development also appeared. These are really just a variation of agile development. Still on the customer-centric pathway, other methods such as extreme programming were developed to improve software quality while also catering for changing customer requirements. Features such as continuous integration, on-site customer refactoring, and simple small releases drove the development of these models. Today, agile systems are in widespread use, and it makes sense because software development is moving so fast that rigid models just can't keep up and would produce software that is unsatisfactory to the customer. Okay, everyone, let's now look at the main topic of the day: the software development life cycle. As we mentioned in the beginning, software development also follows a life cycle, just like every other thing that you can think of in the world. The purpose of using a life cycle in the developing software ensures that it is of the required quality and produced in a timely manner. Nearly all software in the world is now developed using software development methodologies, which all follow the software development life cycle in one way or another. Although methodologies and strategies may differ, the steps in the software development life cycle are pretty much the same across the board. Okay, let's now look at all these steps in detail. The software development life cycle follows a number of stages that are distinct from each other. They are analysis, feasibility study, design, coding, testing, deployment, and maintenance. Okay, let's now look at each of these stages in detail. The first stage in the software development lifecycle is known as the analysis stage. The main point of the stage is to find out if it is a good idea to embark on the project or not. At this stage in the cycle, requirements are gathered from the user, as well as other vital information such as the type of people who are going to use the software package, the type of input the software is going to receive, the data that is going to be produced as output, as well as the setting in which the software is going to be used. The objectives of the project, as well as the user's specifications, are fleshed out as much as possible at that stage. Another important activity in this stage is to identify the available resources, such as developers, the money that is needed to accomplish the project, the equipment that is needed to develop the software, as well as the time that is available. At this stage, communication with a client is vital. If the project is not a completely new one, this is the time that an analysis of what competitors offer in comparison to what the project is going to offer is done. At this stage, the customer's needs are explicitly defined as computational problems. You recall from Module 1 that every computer program starts off as a clearly defined problem. Notice the word clearly here because ambiguity will have you running in circles at a later stage in the development process. We could spell out this stage in 3 distinct steps. Step 1. Requirements gathering is where you gather all relevant information from the user and turn it into computational problems. Step 2. Scope definition. The problems are fleshed out as much as possible. So that's a rough idea of the upper and lower bounds of the software that are apparent. And then step 3. Planning is for quality assurance and the risks involved, as well as potential costs, overheads, and time requirements. It wouldn't make sense to go ahead and spend so much money and effort when you could just walk into a shop and buy a complete software package that caters for your needs. It can't be emphasized enough that thorough planning is required to save time, money, and resources in later stages of the software development lifecycle. At this stage, it is important to define the scope of the project. Although this is not set in stone, setting the scope of the project right from the beginning will help you better plan for the finances that are required, as well as the resources. In case you're wondering, scope refers to the upper and lower bounds of the solution in terms of the problem that it is trying to solve. This is because no single software can solve a set of problems entirely. It'll take an infinite amount of time to build such a software package. Setting the scope ensures that you reasonably cater for the customer's needs while staying within reasonable limits of costs, resources, and time. The next key stage in the cycle is the feasibility study. As the name suggests, you'll be looking at whether it is sensible to continue with the project given all the information that we will have gathered at this stage. At this stage, a document called the Software Requirements Specification, or in short, the SRS document, is produced. It includes everything that is to be designed during the development process. The feasibility study looks at 5 main aspects. These are technical feasibility, economic feasibility, legal feasibility, operational feasibility, and schedule feasibility. At a technical level, you'll be checking if current computer systems can handle the kind of system that you want to develop. It makes no sense to develop a system that supposedly does amazing things, yet current systems can't handle the sheer amount of processing power that is required, or the hardware components that are required simply don't exist yet. The technical requirements also look at what the client has. If you're looking at a small business, you wouldn't expect them to accept proposals that says they should buy a supercomputer to use the software product that you develop. The next aspect of the feasibility study is economic. This looks at the money side of things. We need to make sure that the project can be completed within budget. The budget refers to what the client can afford, as well as what you, the programmer, need to earn. It makes no economic sense to develop a software package that pleases the user but leaves you with a negative bank balance. This typically goes hand in hand with the project scope. Next, we look at the legal feasibility of the project. You may technically and economically be able to finish the project, but is it legal? This comes as no surprise, as we've seen quite a lot of companies fighting legal fires that arose from their software. This could partly be blamed on the changing of times, but could easily also be a result of not doing legal feasibility checks properly. This is a particularly important step. It is just very easy to violate cyber laws and regulatory frameworks, compliances, and policies. This goes from as low as the client's own policies right up to national and international laws. Next, you would look at operational feasibility. This sounds a lot like technical feasibility, but is a more direct aspect of the client's requirements. It looks at whether you can create the operations and processes that are required by the client. The resulting report tells you whether the correct resources and technologies that are required to complete the project exist. It also analyzes the technical skills and capabilities of the people that will be involved in the software development process. It will also look at the degree of difficulty of maintenance and upgrades at tertiary stages. The last and probably the most obvious part of the study is the schedule feasibility. This is where most computer scientists are guilty of not doing things properly. Schedule feasibility looks at the timelines and deadlines which will be followed in the course of development. This makes sure that each stage of development is given a fair share of the developer's time without sacrificing quality and deliverables. This is one of the most crucial components of the feasibility study, as it will determine whether the project will be completed in time. It is especially important nowadays because software is now being developed so rapidly that if your project takes too long, it may already have been overtaken by the time you release it. Think of all those apps that you think are so awesome, but no one uses them because apps came before them and became way more popular. It's hardly the case if you have a client that you are developing an app for, but it is quite possible that the client will get frustrated and walk away. Ouch. The feasibility study will give you a pretty good picture of the direction in which the project will go at a high level. You can pretty much tell by just looking at the feasibility study report whether it is sensible to go on with a project or not. Now imagine what would have happened if you had just jumped onto a computer and started writing code. It would be pretty disappointing to produce a software package that is irrelevant to everyone, and so it is not used. This could be said for quite a lot of apps that you find in your device in App Store that provides similar functionality to some other already popular apps, but do so in a fairly disappointing way and are hardly ever downloaded. You're pretty much guaranteed to fail if you don't do a proper feasibility study. After completing the feasibility study and determining that it is sensible to go on with a project, the next step would be the design phase. This phase comprises two main documents, namely the high-level design document and the low-level design document. Now, this is where you'll come up with pseudocode and flowcharts that pretty much lay out your solution in a logical manner. Let's look at each of these documents in a bit more detail. The high-level design document contains a brief description of each module that is going to be contained in your solution, along with the proposed name. It also shows diagrams that shows the interface relationships and dependencies between modules. In case you're wondering what that is, it's just a fancy description of a flowchart. If your software package is going to include a database, tables are identified along with key elements. The functionality of every module in the solution is outlined. The document also shows diagrams that outline the architecture of technologies that are going to be employed in this solution. The low-level design document contains all the functional logic of the modules, database tables which are quite reasonably fleshed out. This includes the types of tables as well as their size. The user interface is extensively detailed, highlighting key user interaction points and design elements. Any error messages that will be presented to the user or logged as debugging information are documented. The inputs and outputs that we gathered in the first stage are paired up with the modules that will be handling them and documented as necessary. The high-level and low-level design documents will be the base on which the actual code is written and tested. These documents also extensively reflect the user's requirements and scope. The next stage is where people usually want to rush to, writing the actual code. By referencing the high-level design documents and low-level design documents, developers now set out to write the actual code that will be implemented in the solution. If it is a large solution, modules are split up into units and assigned to teams of developers. Typically, this is the longest phase of the life cycle. Constant references are made to preceding documents, such as the requirements documents and the design documents. So are the scope and the limitations that will have been set prior to this stage. The programming language will have been chosen prior to this stage, according to the feasibility study. Naturally, the next phase after coding is testing. The code is deployed into the test environment, which mimics the real environment in which the software will eventually be deployed. Testing is carried out using various strategies, such as black box and white box testing, to name a few. We will look at these more closely in Lesson 5, so we'll just touch on them briefly now. Black box testing entails testing the system at a high level, which mimics what the user will experience. In this method, the behavior of the system at an external level is scrutinized. This is where errors that are likely to be noticed by the user will be picked up and rectified. White box testing looks at the internals of the program. The logic, functions, and relations within the system are extensively tested, and if any bugs are found, they are rectified. The errors that are picked up in white box testing will typically not show directly to the user, but rather show up as inaccuracies in the program's execution. This stage aims to remove as many bugs as possible. But as we all know, as the scale goes up, it becomes increasingly difficult to create a completely bug-free program. The main quality checks are done at this stage. This is not to say that quality checks are not done on prior stages. It is only that at this stage, there is something tangible to quality check. After extensive testing and rectification, the team releases a satisfactory completed software package. This package is then sent to the client for installation or deployment. The software testing stage is not completely over, as there could be new bugs that could be found on site and not in the testing environment. A pilot test is run to see if the system is running as intended. And if everyone is satisfied, that is, the developers as well as the customer, the system is then commissioned. After commissioning, the customer starts using the new system, but there are still 3 activities that developers carry out. Preventative maintenance. As we mentioned, it is not really possible to create a large software package that is completely bug-free. Developers from time to time release bug fixes to remove these discovered bugs. Developers also carry out their own background testing just to see if there aren't any more leftover bugs. Any code that is at risk of being broken by new operating systems is adjusted accordingly. Developers also optimize the structure of the program so that it runs efficiently. Perfective maintenance. Most modern software development doesn't end with deployment. Developers come up with new features that are then added to the existing software. These new features can come from user suggestions or from the developers themselves. And then we have adaptive maintenance. Developers also add new underlying code without necessarily changing the underlying functionality of the software or adding new features. If there is a more efficient way of solving a particular problem, the developers then integrate that your way into the existing software. Developers could, for example, change the user interface so that it matches a current version of the operating system. The software package pretty much sits in maintenance for the rest of its life, up until it is decommissioned and replaced by something else, or just simply becomes obsolete. There are quite a lot of models that are used in following the software development lifecycle. The most popular is probably the oldest as well, as mentioned earlier, and that is the waterfall model. We already spoke about the waterfall model, which was the earliest model that was used in software development. It was built on the premise of clearly defining each step of the software development lifecycle with clear objectives and well-defined milestones. This diagram shows how the waterfall model executes the software development lifecycle. The waterfall model takes each of these stages as a separate process. A subsequent stage can't start until the preceding stage hasn't finished. Each stage has its own deliverables, that is, a set of tangible results and milestones that are achieved. The waterfall model is arranged in a sort of waterfall, hence the name. It is centered on quite a lot of rigid aspects, such as the project is short. It has requirements that are very well documented and fixed. The definition of the product is stable. The technology that is used in the implementation and design of the system is stable and not dynamic. And resources are abundant and the required expertise is at hand. The waterfall model has quite a number of advantages as well. It is a simple model which is easy to understand. Each of the phases are completed one after the other, which makes everything clearly defined. Tasks are easy to arrange and distribute. It also generally produces a well-documented process. The waterfall model has quite a number of advantages as well. It is a simple model which is easy to understand. Each of the phases are completed one after the other, which makes everything clearly defined. Tasks are easy to arrange and distribute. It also generally produces a well-documented process. This all sounds awesome, but it's not without its disadvantages. There isn't any software to talk about until quite late into the production lifecycle. This is the direct effect of producing a lot of risk and uncertainty, and problems are often undetected until it's too late. It's not a good model for complex or object-oriented projects and doesn't really work well for long and ongoing projects. If requirements change a lot, it'll be difficult to keep track of things. Things such as adjusting the scope are near impossible as you'll have to adjust every other component of the project. The V model is an extension of the waterfall model. It is also known as the verification and validation model. Each of the steps in the V model is based on the premise that the corresponding testing phase is associated with each of the stages in the software development lifecycle. This diagram shows how the V model works. The model has the actual system development at the center, and each of the stages correspond to one of the later stages after writing the code. The V model has the same applications, advantages, and disadvantages as the waterfall model. As you can see, the testing is carried out in 4 stages. Unit testing. Code is tested at an early stage, module by module, to eliminate bugs. Integration testing. This tests the communication of the various components of the program. Then we have system testing. This phase tests the functionality of the entire software package to check for hardware and software compatibility. Then we have acceptance testing. Here, the software package is tested for compatibility on the host system to see if it'll work well with other software that is already on the end user's system. The iterative model, as can be seen in this diagram, attempts to solve the problems that are encountered in the other two linear models by implementing a small subset of the requirements, then iteratively builds the rest of the package until all the requirements are met, as can be seen in this diagram. The fact that more than one iteration can be produced at the same time quickens the software development process as each iteration builds on the previous. The requirements for the system need to be clearly defined and understood. It does allow for a bit of requirement evolution, but mostly for the minor requirements. It also allows for changes at various stages, including the goals. It has several advantages over the first two models. Its strengths include the following. It allows for quick development of functionality quite early in the process. It also supports parallel development, and changes to the scope are less costly. The really good thing about the iterative model is that at every stage, there is a functional product. The model is not without its shortcomings, though. Requirements are not as extensively gathered as they are in the two previous models. Also, because there's quite a lot more going on at the same time, management needs to be executed carefully. Also, it's kind of a waste of time when working with small projects. It also requires quite a lot of skill for risk analysis. Another model that falls under the iterative model is the spiral model. This diagram illustrates how it works. The spiral model is quite popular in software development because it mimics the natural development process of a lot of things. It is essentially a mishmash of the linear model and the iterative model, with a lot of emphasis on customer feedback. Based on the customer's feedback, each section of the spiral model has its own little waterfall model inside. At the end of the little waterfall, customer feedback is gathered and implemented into the next section of the spiral. The spiral model is a good method to use when there is a tight budget and risk evaluation is particularly important. It requires long-term commitment because there are a lot of potential changes to the economic priorities as the requirements change over time. It is also used where significant changes are expected during the development cycle. The spiral model has the advantage of comfortably accommodating changing requirements. Users get to see what is going on in the development cycle quite early on, and so can provide the relevant feedback. Development can be divided into small chunks which can be better managed. In terms of the spiral model's shortcomings, things such as time management can become pretty complex in the spiral model, and it's not suitable for small and low-risk projects because it works out to be more expensive. Because of the sheer number of iterative processes, it produces quite a lot of documentation, which may be difficult to keep track of. Now, we've already seen a pattern where nearly all the software development strategies follow the 7 basic steps that we discussed at the beginning of the lesson. There are other models that take a completely different approach and deviate from these 7 steps. In some models, such as the Big Bang model, there might not even be any planning at all. It is literally just the classic throw money at the problem scenario. Let's look at some of these methods in greater detail. A common word that pops up whenever you talk about software development is agile development. It is pretty much exactly what it sounds like. Agile development is built upon the iterative development process's requirements, and the solution evolves through collaboration of cross-functioning systems. Agile software development is typically used in development frameworks such as Kanban, extreme programming, and feature-driven development. Agile development is basically a collection of models that follow the principles that we are going to discuss here. Agile development is based on the 12 principles and values that are aligned in the Manifesto for Agile Software Development. The 12 principles that are defined in the Agile Development's Manifesto are: customer satisfaction by early and continuous delivery of valuable software. Welcome changing requirements, even in late development. Deliver working software frequently, weeks rather than months. Close daily cooperation between business people and developers. Projects are built around motivated individuals who should be trusted. And then face-to-face conversation is the best form of communication. Co-location. Working software is the primary measures of progress. Sustainable development, able to maintain a constant pace. Continuous attention to technical excellence and good design. Simplicity, the art of maximizing the amount of work not done, is essential. Best architectures, requirements, and designs emerge from self-organizing teams. And number 12, the team regularly reflects on how to become more effective and adjusts accordingly. Here is a table comparing a modern agile model with the older, more traditional waterfall model. Earlier models are often referred to as heavyweight programming methods, while agile methods are referred to as lightweight models. Here is a table that summarizes this. Agile model, an incremental and iterative approach to software design. Waterfall model, development of the software flows sequentially from start point to end point. Agile model, the process is broken into individual models that designers work on. Waterfall model, the design process is not broken into individual models. Agile model, considered unstructured compared to the waterfall model. The waterfall model has a rigid structure. The customer can only see the product at the end of the project. With the agile model, small projects can be implemented very quickly, but it's hard to estimate development time for large projects. With a waterfall model, it is very plan-orientated, so it is more secure. With the agile model, errors can be fixed in the middle of the project. But with a waterfall model, problems are often detected when it's too late. With the agile model, the development process is iterative and the project is executed in short 2 to 4 week iterations. And with the waterfall model, the development process is phased. And the phase is much bigger than iteration. Every phase ends with a detailed description of the next phase. With the agile model, documentation attends less priority than software development. And with the waterfall model, documentation is top priority and can be used to train staff and upgrade the software with another team. With the agile model, every iteration has its own testing phase. It allows implementing regression testing every time new functions or logic are released. And with a waterfall model, the testing phase is executed after the development phase because separate parts are not fully functional. With the agile model, when an iteration ends, shippable features of the product are delivered to the customer and are usable right away. But with the waterfall model, all features developed are delivered at once after a long implementation phase. With the agile model, testers and developers work together. And with the waterfall model, testers work separately from developers. For the agile model, user acceptance is performed at the end of each sprint. And for the waterfall model, user acceptance is performed at the end of the project. The agile model requires close communication with developers to analyze requirements and planning. With the waterfall model, developers does not get involved in requirement and the planning process. This results in time delays between testing and coding. You may want to snap and save this table to refer to later. Agile development consists of a number of processes that are used to speed up software development. These include methods like Scrum, Crystal methodologies, dynamic software development methods, feature-driven development, lean software development, and extreme programming. As mentioned earlier, these methodologies are built upon the iterative development process to dramatically shorten software development time while producing deliverables at each stage. This is especially important given the pace at which software is evolving nowadays. There is really no time to sit in a project for months or even years on end, whilst expecting to release a fresh, new software package at the end of such a long stretch. Agile development methods are now commonplace, even with large projects like operating systems, as they allow a far shorter turnaround time while still allowing the development of high-quality software. It would be pretty incomplete to talk about software project management and not talk about these 7 sins that are the root causes of project failure, as described in the Agile Manifesto. They are obscurity, insentience, tardiness, lethargy, inevitability, obsequiousness, and evolution. Okay, let's look at each of them in detail. When the project plan is not clear, we can't really be sure what we're hoping to achieve, and it is pretty clear that there will be no goals in sight. Goals should always be measurable, specific, actionable, realistic, and time-based. Communication is of paramount importance in making sure that project goals are as clear as possible. Any lack of urgency in most aspects of life is always a detrimental habit. The project should be planned while there is still time, and clear timelines be set to deliver the project in time and make sure that the project is of the desired quality. It can also set in when the people who are sponsoring the project don't really believe in the goals and vision of the project, and this stifles communication. Insentience refers to lacking consciousness. If the project is led by incompetent people, it often just stumbles from milestone to milestone with no real vision and is most likely set for certain failures. When projects lack clear communication channels and very little is known about them outside the development team, they are often stillborn. This is when a project's milestones are not considered with the seriousness they deserve. Deadlines are not met, and the team continues as though nothing has happened. This is very likely to spark frustration on the customer side, and such projects might be dropped suddenly. Typically, with sloppiness on milestones comes poor quality, and if the project somehow manages to make it to the end, it will be a far cry from the desired output. Obsequiousness refers to servile obedience and excessive eagerness to please. When the project manager fails to exercise their authority to keep things on track, this leads to problems such as scope creep, budget blowouts, and missing milestones. It is a responsibility of the project manager to make sure that the resources are allocated as and when needed, and the project is quality checked at every step. Inevitability refers to something being certain to happen and unable to be avoided or prevented. An example of this would be if the project is executed without paying attention to risk. Risk is like a coin. On one side, they are positive risks, which foster innovation, and negative risks, which can spell doom for the project. If both are ignored, you can be guaranteed that the end product will be a lukewarm product. This is one of the biggest problems with software projects. Without due care, the scope can creep beyond what team resources and finances can ever take into account. It must always be top priority to make sure that there is a balance between the quality of the project and the available resources.